This for people that miss class. Hopefully this is helpful to them. It is not to take place of you taking notes and stuff like that. It's not going to be as beneficial as coming to class because you're going to miss stuff because you see it that is stuck just to that projector. It's really the only thing that I can do to make it really visible and easy to read. I tried to have it set up so I could see the whiteboard and the projector, but or smartboard, but you can't. So there are things that we do in here that it's going to be very beneficial to try to be here as much as you can. Take notes, ask questions, that kind of stuff. But that's meant to kind of help those people that can't. Yesterday, I think we closed class. We talked about this stuff, right? You can't see it, through. We finished talking about these basic definitions of acute angles, right angles, obtuse angles, straight angles. Those are going to be things that, like I said, hopefully are not new to you, but we do need to know them, have the same understanding of what they are, because they are going to be used in other definitions, they're going to be used in other properties, so it's very useful that we know those. I think the one that probably is least familiar to you is the straight angle one. Something that I want you guys to know as well, and you're going to see this in your homework tonight, maybe you've already seen it. If I draw an angle like that, okay, is that a right angle? Why not?
You don't have the little square thing in the corner.
Okay, I don't have the notation in there to identify that it's a right angle. Okay, it might look to you like a right angle. All right, and I might have obviously drawn it by hand. I'm not really good at that, but if I was able to really narrow in and try to get those to be as perpendicular looking as possible. So for instance, maybe I do it here, so you can use straight lines here. Maybe I do that and maybe that. Okay. Now if you look at those might look to you like they're perpendicular, like there's a right angle there, right? But your eyes can't tell the difference, okay? And that angle might be 89.99999 degrees. Well, that's not 90 degrees. Does that make sense? It could be 89.1 degrees. Well, it's very similar to 90 degrees. Your eyes probably can't tell the difference really between like 5 degrees. You probably couldn't tell the difference between an 85-degree angle and a 90-degree angle based off just the way it looks, okay?
What's that,
1/4. So this becomes important throughout the rest of the year. You do not want to take and make assumptions about a picture or make assumptions about really anything until you've been told explicitly what's going on. So if I told you I have a friend named Pat, do you know anything about Pat? No, just that I'm my friend and probably not maybe the smartest person because they're my friend. Okay? But you don't know anything about them, so you don't want to make assumptions about them until you see them and say, oh, Pat's a guy. Okay? When I said the word Pat, did anybody think of a girl? Yeah, so you don't want to make assumptions. So when I see that angle, I don't want to say it's 90 degrees until somehow I'm told that. Okay? Now it's a 90-degree angle, now it's a right angle. And there will be other ways that we learn something to be a right angle. The way some segments interact with other segments, maybe definitions and stuff like that will help us maybe put that mark in there on our own. It doesn't have to be there at the onset of the problem, but we can't make assumptions about things. Okay, so there's a question in your homework tonight or last night, if you started it last night, that kind of looks like this. And it looks like you got 2 right angles there, right? Okay, but there's no markings in it. And it asks you to answer some question about one of your classmates made an argument that those are both right angles, or that they're both congruent to one another. Okay, and you had to talk about why your classmate was wrong. Okay, well the idea is that if that's this could be 89 degrees if we actually put a protractor on it, and that could be 91 degrees, right? Okay, or this one could be 89.0001, and this could be 90.999999. Okay, so we cannot tell until somebody tells us that, that angle is 90 degrees, that angle is 90 degrees, now they are congruent. All right, so make sure that throughout the entire course, and there's going to be a lot of different times that we see that, that we want to make that argument and remind ourselves, are they providing that information so I can make that conclusion. The next thing we'll talk about is what we call the protractor postulate. The protractor postulate is exactly the same as what the ruler postulate said last week. Okay, the ruler postulate said basically we're going to be able to take any point off a number line and give it basically an address, give it a location, give it a number associated with this point. Okay, and then vice versa, any number on the number line has a point. Okay, so we talked about that one-to-one correspondence, that any point has a number, and any number has a point. What that allows us to do is create that ruler, and then we can measure segments. And we talked about that last couple days. The protractor postulate does the exact same thing. Okay, but now instead of looking at an entire number line, we're really going to just focus on the numbers between 0 and 180. Okay, because those are the angles that we're going to be familiar with and deal with early on in this course. Okay, so we said that every number between 0 and 180 can get paired with, instead of a point now, we're going to pair it with a ray. Okay, and then every ray can be paired with a value of 1 or 0 to 180. Okay, and what happens then is, and we put that number line, that 0 to 180, we curve it around the circumference of a circle, and obviously we want to get the semicircle here. But that allows us then to find the measurement between two rays. Okay, it helps us find the angle. So this here, okay, is on my website, but this is an applet that's going to kind of allow you to mess around with this and get a good understanding of how to deal with a protractor. When you guys were like 7th and 8th grade and you talked about using protractors, you probably became accustomed to doing this. Rotating your protractor, getting one of the rays to line up with 0, right? And then you kind of come out here and say, okay, this lined up with 0, this one's going through what looks like 65, right?
Yep.
So 65-degree angle. And that's what we're seeing there, correct? Okay? But that's the same thing that we talked about the other day in regards to a ruler. We don't always have to start at 0. Okay? We don't always have to put the end of our tape measure at the end of the object that we're measuring. We could have started, put the number 5 on the end of our object that we're measuring, and then roll out our tape measure from there. So same thing happens. When you see a protractor, you don't have to start at 0. Okay, I'll talk about why it's convenient to start at 0, but you don't have to. We could come up here and say, okay, this number here, okay, what is the value? Let's talk about just the top row, okay, top row of numbers. What is the value that red ray is going through? What's the coordinate of that? That's 120 and that's 130. It's got to be 125, doesn't it? Okay. Yeah, I see here. You guys can just throw out answers. Okay. So 125. What's this ray AC going through? 60. Okay. Those are in their degrees, but those are the coordinates that are paired up with those rays. And that's what we're talking about. Every ray has a coordinate. Every coordinate has a ray. All right. So then the difference between those, just like we did with distance the other day, if I take the absolute value, and it doesn't matter the order, so let's go 60 minus 125. Okay. If I do that subtraction, that gives me the absolute value of negative 65, doesn't it? And what's the absolute value of negative 65? 65. Okay. Now you could have done it this way. You could have gone, maybe some of you will always, and this is kind of what I do on my own, I always put the larger, and I know I'm taking absolute value, I always put the larger number first anyways. I just think I'm more accustomed to going and removing from a larger number. So that's going to give me the absolute value of 65, which is still just 65. And like I said, that is exactly what we were seeing over here. And it doesn't really matter where you put your protractor. Now my protractor kind of looks like it's maybe horizontal to my desk or horizontal to the bottom of the smartboard here, but it doesn't matter. Let's say that we've got something kind of like that. Okay. This looks like it's going through maybe 67. You guys agree with that? 67 degrees. And this one looks like it's going through 132. Okay. Well, if I subtract those, what's 132 minus 67? Still 65. Okay. It doesn't matter the starting point. You know, I could go 10 and 75. Still get 65, right? Okay. So that's how you can use a protractor. Now it's convenient to do this because here's the rule for finding an angle. You take, you know, if this coordinate is B and that one's A, okay, some arbitrary values, you go B minus A, you take the absolute value. That should be consistent with what we do with the ruler. Okay, and the ruler postulate, finding distance on a one-dimensional line segment. I think if you look in the PowerPoint, it uses C and D, but it doesn't matter. When you do that, isn't it so much easier to do subtraction when this number here, or that number, doesn't really matter, is 0? Isn't it really easy to take 65 minus 0? And you get the absolute value of 65. So that's why maybe in 7th or 8th grade, when you guys physically had that protractor, they taught you how to line it up that way because maybe they thought that we weren't at the level yet to really explain the protractor postulate and the ability to find angles regardless of your starting point. And that's kind of what this course is about a lot of times, is that you already know a lot of the things that we're going to talk about, but we're going to look at them from a different perspective. We'll kind of dig into them a little bit deeper, and that's just one of them. Is that doable? All right. At some point this week, I'll give you maybe an in-class assignment, Cameron, that I grade for right or wrong. And on that in-class assignment that I grade for right or wrong, I'll give you a picture that kind of looks like this, where we've got a bunch of different rays on there. Okay? And I'm going to ask you, can you find the measure of angle, maybe FAB? Okay, which if I look at FAB, okay, it's going to be the angle between those two rays, right? So I look over here, well, that ray, AF, looks like it's going through 25. B looks like it's going through, like I said, what's that, 126-ish, 126, 127, and then I do that subtraction, right? Okay. And then I'm going to ask you in the same picture, can you find angle CAB? Can you find CAG and stuff like that? Okay. So I'll ask you 4 or 5 different angles from that picture. Is that all right? And you won't have a protractor. It's going to be a static picture. You can't move this. Okay. And hopefully that picture will then get you to realize that you don't need a starting point, okay, of 0. You can go anywhere that you want. Start with anywhere you want, anywhere you want, and then the difference is going to be your angle. Is that all right? Okay. A lot of times when we talk about an angle, the way I want you guys to kind of visualize it is it's the span. You know, if I look at this angle right here at 48 degrees, I want to say if I had 2 rays that were on top of one another, okay, and I start to move one of those rays away from the other one in a particular direction, that span of how those 2 rays open up is the measurement of 48. That's the angle that we're talking about. Does that kind of make sense? Okay. So you might hear me say that word of span, and that's just how far that angle is opening up. All right. So that's protractor postulate. So what's nice now is that basically with that postulate and with the ruler postulate, we have the foundation to measure pretty much anything that we want to in this course. Okay, and that's what this course we talked about. Did we talk about what geometry really means? Geo meaning earthly, metry meaning measurement. So through earthly measurements. We talked about the first day. Okay, so you were paying attention?
Yeah.
All right. So once we are able to talk about distances and angles, we have pretty much every single measurement that we need for this course. All right, we'll start talking about arc lengths, eventually in arc measurements, but that directly links itself back to angles. Okay. Just some notation stuff. If I want to talk about things being congruent, angles being congruent, just like we talked about with segments, If I have two measurements, let's say I have two angles that are both 30 degrees. Let's say I say measure of angle 2 and measure of angle 3 are both 30 degrees. So that says their measurements are equal. So measure of angle 2 is equal to measure of angle 3. Maybe they're both 30 degrees, like I said. If I know they're both angles and I know they're both the same measurement, then we can draw the conclusion that angle 2 is congruent to angle 3. And that's just the notation we use to say that they're congruent. And remember what that means is that if I have the picture of angle 2, I could cut it out like a cookie cutter, lay it on top of angle 3, and they're going to match up perfectly. Does that make sense, everybody? Okay. Alright, and this is not, if you're using the PowerPoints for your own use, okay, obviously we're not looking at those today in class, but if you go back to the PowerPoint and open it at home, it's not going to have this slide in it, okay? Adjacent angles, okay? And there is another PowerPoint later on in the chapter that talks about adjacent angles, but it's going to be useful to talk about now. What's the word adjacent mean in everyday English? Like, how would you use that outside of this class? Cameron?
Like the opposite or the same. You know the opposite?
Not quite. I'm adjacent to you.
Taller? Closer?
Now I'm adjacent to Jenica. But now, I'm not adjacent to either of you. That's kind of, if we're talking about English everyday use, so you said what? Close. Okay? So everyday English, next to might be close to, or next to, might be how you use the word adjacent. Okay? Or beside, or something like that. If you're talking about like properties, okay? Like you have neighbors at home, right? Okay? Your lot, you have your lot that you live on, and then the lot next to you is referred to as the adjacent lot, okay? Because they're right next to each other, side by side. They share kind of a boundary. Does that make sense? Property boundary. So same idea when we talk about angles, okay? But we have to have some mathematical components to it. It says adjacent angles are two angles, okay, that share a vertex. We talked about vertices yesterday. They share a common side or a common ray. We talked about that yesterday, what those were, what rays were. And they have no interior points in common. What did she say?
Something about Trey.
You need to unlock your iPhone first.
Huh. I guess I asked Siri a question. I don't know. Alright, so two adjacent angles, common vertex, common ray, and no interior points in common. And it's really important that we satisfy all three of those conditions. So I'll give you some examples, some visuals here of situations in which we have adjacent angles and situations that we don't have adjacent angles. And it's going to be important to be able to identify them because throughout the year we'll have rules that say this only works with adjacent angles, this works with non-adjacent angles and stuff like that. So it's got to be, it's going to be pretty important that we're able to recognize those things. I look at these angles up here. Right now I've got three angles. I want to kind of do this. Let's just look at, let's make these two rays overlap each other. So now we just have two angles there, right? We've got a blue angle and a yellow angle. Okay? Do they both have the same vertex down there at the bottom left? Yes. Okay, and that vertex is A, right? Okay. Now when we talk about the interior points overlapping, okay, or being common, the reason I shaded these blue and yellow is because the blue one, everything that's blue represents all those infinite points we talked about yesterday being on the interior, right? Okay. So, you know, just kind of going back through, those would be all interior points. And if we highlighted all of them, the infinite amount of them, it would just create that angle that's all blue, right? Okay. These points over here would be the ones that are on the interior of the yellow. And this one should be blue. Okay? So the idea then is none of those blue ones are in the yellow area, and none of the yellow ones are in the blue area, right? Does that make sense? Okay? So I'll never be able to pick a point out that is yellow and say that it belongs to the interior of the blue angle. I'll never be able to pick a blue one out that says it belongs to the interior of the yellow. So that means they don't have anything, they don't have any interior points in common. There's no overlap. Does that make sense to everybody? Okay. They also share then the common ray A to D. Okay? So ray AD here, or C, yes, whatever you want to call this ray here in the middle, okay, AD or ray AC, they share that. So we met all three criteria for those things to be adjacent. All right. So now if I go back to the way the problem started or the picture started, do something like this. Okay. Do they share a vertex? Yep, they still share A, right? Are any of the blue points overlaying into the yellow? I don't know why that did that. No. If you're in Math Excel for too long, it kind of kicks you out, I think. So are none of the blue points are in the yellow? Are any of the yellow ones in the blue?
Nope.
No, so they have no interior points in common. So we've satisfied two of the three conditions so far to be adjacent. But do they share a common ray? No, they don't have a side. The blue one, has these two sides, AB and AC, but neither of those sides are the sides over here, AD and AE. Okay, so we need all three components to be adjacent, so the blue one and the yellow one are not adjacent. Does that make sense? Okay. If we do something like this, okay, so we had the blue angle, and now we put the yellow one in, and you can see the kind of the color change, right? Okay, so where that's that grayish yellow is the overlap. Okay, so what we're saying there is that one of these yellow points, or two of them, or actually ends up being an infinite number of them, we've got some yellow points in here on the interior of the blue. Does that make sense? We've got overlap. We've got blue ones and yellow ones in the same region, so we've got overlap. We've got points that are on the interior that are in common, and that's a problem. That violates the idea of adjacency. Okay, so those two angles, DA to E, angle DAE, and angle BAC, hopefully you can visualize those, see those, they overlap there where it's gray, okay, or yellowish gray. They still have the same vertex, okay, but they don't share a common side either. Okay, so there's two reasons why those would not be adjacent. Is that doable? All right. So our goal then is, I'm going to use that word adjacent. Okay, it's really not extremely prevalent if you were looking at the textbook or look at the. I don't think it uses the word adjacent in Math Excel or anything today. But you might hear me say that word, and I want you to make sure that you understand what it means. And we'll come back to it again later next week. Sorry. Alright, so that gets us to the angle addition postulate, which is very similar to the segment addition postulate, right? Okay. Segment addition postulate said you had to have a series of points aligned in a particular manner that developed smaller portions of a larger segment, and then you added the smaller chunks up to get you the total, right? Same thing's going to happen with angle addition, okay? You're going to have some angles, you're going to have some points and rays, and they have to be orientated.
On the web about the points how long will smaller portions of a larger add of the smaller. Check it out.
Huh.
It's very dumb.
You just can't hear me in there. So we have to have a particular orientation of these parts so that this rule that they're providing us really works. Okay? And the key part here is that they say point B is got to be on the interior of angle AOC. Okay? Because then when that happens, we're able to get AOB, which they're showing as the yellow angle, plus then BOC, which is the blue one. If we add those together, hopefully you guys recognize that that's going to give you the total from angle AOC. Alright? Now, a lot of the problems that we do are going to focus on working with basically just two angles like this, but you can put a third one on here. You can put a fourth one. When we get to circles, we'll deal with like 8 to 9 to 10 that we add together. But it's just simply adding adjacent angles one after another until you get your total. Okay?
Another way of visualizing it, maybe so it's kind of dynamic, is this idea here. If we have, let's see here, oh. All right, so we have just some angle of 66 degrees, okay? Well, that angle of 66 degrees can be broken up into smaller portions, right? Smaller sections. So let's go ahead and do that. If I put in that ray there, I can break it up, and I can break it up in any way I want to, okay? But when I click this button, it's going to show me maybe how it's broken up there, where it's 37 and 29, still adding those two smaller portions, the red and the blue together to get me the total. You know, I could come down here, and I could have 59 and 7. If I still add them together, I still get the total of 66. Okay? So the angle addition postulate is saying, no matter where this point D shows up, okay, we're going to add those two things together. But D has to be on the interior of ABC. Let's see what happens if I move it out here. See how I move it out there, and now it gives me an angle of 125 and an angle of 59. And do we know that does that equal 66? No. So we would kind of break the applet here, break the program. But the reason is, think about this. If I just say, going back to this picture here, if I don't give you any criteria on where B has to be, I just say that, you know, B is a point that exists. So let's say that we start with, just kind of draw it down here. Let's say we start with A, O, C, but now I put B over here. Now I've got that ray. But I try to follow this that says AOB, which AOB is going to be this green angle, plus BOC. Well, BOC now is that red angle. So think about adding the green angle to that red angle. They're saying those two angles added together should give me AOC, which is that blue one. And hopefully you recognize that that is not a valid statement, because the sum of the red and the green is so much bigger than the blue one, right? So it's important where that point shows up. And we talked about that with segments. When I gave you, let's say A, B, and C, let's say A, B, and C, A, B, and C are collinear. Then we said something to the effect that AB plus BC equaled AC. Okay? But that does not work if I don't have any criteria on where A, B, and C relate to one another. Okay? Hopefully you recognize that, you know, if A, B, and C are in this order, then yes, that makes sense. A to B, add to it B to C, should give me the total, right? But if I reposition those points, if I put B there, put A there, put C there, they're saying A to B, that distance there, plus B to C, that distance there. If I add those two together, this is saying that I should get that total there, which we know would be false, right? So the key thing is that we have to tell you where B is, all right? We have to tell you B is between A and C. And that was the key thing when we talk about the segment addition postulate. So it's the key thing here when we talk about the angle addition postulate, about where B has to be in regards to that interior. Okay? Does anybody have questions on the kind of the theory or the idea, the concept behind angle addition? All right, let's do some examples. All right, if I've got this thing here, and this is, you see these types of questions in your homework where they put everything in the picture that you need. Okay, hopefully you guys are recognizing that this angle ROS is the angle that we're going to start with. Okay. So we'll take 4x minus 20, and that's going to be one small component. Okay. Then we've got this 3x plus 14. Okay, you guys agree that those are right next to each other? They do not have any overlapping points. Okay, so no common interior points. They share the same vertices O and they both have the same ray OS. Okay, so those are adjacent angles, so we can add them together. What should they total? 155. Okay. That's going to give us how many x's? 7x. What's the constants change to?
-6.
-6 equals 155. So 7x is equal to 161, right? Now last class I asked, how do you do that fast? How do you do that division fast? That's the next step, right? Somebody said grab calculator. Okay, how do we do it in our head fast? How many times, look at this number here. Look at, basically what you want to do is go left or right here and start thinking of whether that number 1 is big enough for 7 to go into it. Is it? No. So now I go 16. Is 16 big enough for 7 to go into?
Yes.
Yes, how many times?
Once.
Twice. So 7 goes in 2 times. That's a total of 14, right? Okay. So we know that it goes in twice. Okay. Gave me a total of 14. 7 times 2 is 14. 16 minus 14 gives me 2 left over, right? A remainder of 2. Tag on that 1 to that 2. So that gives you 21, right? How many times does 7 go into 21? 3. Okay. Now it's a long time to explain that. Okay, I mean 35 seconds to explain that. But you start doing that kind of stuff on a regular basis, okay, in your homework and stuff like that, you're going to become very proficient in dividing weird numbers, okay, numbers that you're not seeing on a regular basis, okay, without a calculator. All right. Now, that's not what we wanted. We wanted RQS. So what do I do with that number to find the measure of angle RQS? Or RQS. Plug it in. So come up here to 4x minus 20. I put 4 times 23 minus 20, right? Now somebody in last class said, I don't know how to, I can't do 4 times 23. Okay? Hopefully they were just kidding with me, but you know, can I do it this way? Can I go 4 times 20 plus 3 that way and do the distributive property? What's 4 times 20? 80. What's 4 times 3? 12. What's 80 plus 12? 92. Okay? So the hope is that you guys eventually be able to do that real quick in your head without having to write anything down. And we see that's 92 minus 20, which is 72. Okay? Come over here, do the same thing. 3 times 23 is 69 plus 14. What's that going to be? 83, right? Okay. Not only do I want you guys to learn geometry and brush up on your algebra skills, I want you to become confident in being able to multiply, add, subtract, and divide just regular old numbers. Okay. Because someday, does everybody want to have maybe a family someday? Okay. Wouldn't it be nice to, you know, your kid comes home from 5th grade, 6th grade, and asks, "Hey, Mom, what are these 2 numbers when I'm all coming together? Dad, how do I divide these 2 numbers?" And you be able to tell them that. Okay, I think maybe some of you say, "When am I going to use this math? And when do I need it?" Think about that kind of stuff, because it's kind of a pain in the butt right now as a student. Maybe you go to mom and dad and they can't help you, right? But when you have kids, wouldn't you want to be able to help them? Okay, so they say, "Well, figure it out on your own," or something like that. So maybe that's a reason. Or maybe your kid comes home and says, "Mom, what's 4 times 23?" and you don't know it. What's your kid starting to think about you now?
There you go.
Yeah, mom's not very bright. Okay, so hopefully we brushing up on those skills, and at least our own kids don't think maybe we have some cognitive issues. Let's do this one. Do this one on your own real quick, and then we'll talk about one more. We won't do one more, but we'll talk about it, and you'll get out of here. All right, as you guys walk through it, just make sure that you're paying attention, because they do this on purpose. A lot of questions, maybe the first 4 or 5 that you do, you'll recognize, oh, they say these parts in order, so I can just take the first 2 things, add them together, so them equal to the third expression, or something like that. And they'll do 3 or 4 like that. But then the next one, they change the order of the components. And people just see the first 2, add them together, so them equal to the last one. I don't know, I've had students in the past for weeks, that's all they did, is they take the first 2, add them together, so them equal to the last one. Make sure you're paying attention, you're inputting things in your picture. They say UTH is 50 degrees, right? So I highlight that, put it in my picture somehow, so I can visually see that that's 50. Same thing with HTS being 6x plus 6, plug that in my picture. Now I recognize that the red angle and the blue angle are the ones I want to add together, and they're going to give me then a total of 13x, which is that green angle, right? Okay. Make sure that you're drawing pictures and stuff like that and inputting information, because it makes things so much easier than just trying to develop an equation from the text. You tell me the answer?
Yeah.
What's the answer?
54 degrees.
54 degrees. You guys agree with that? Yeah, when we get down to what's going to become 50, we get 56 is equal to what, 7x?
Yep.
So x becomes 8. We're going to plug that in. 6 times 8 is 48, plus 6 is 54 degrees. How can I check that?
And
Go ahead. Okay, add them together so I get 104, right?
yeah.
But is there a 104 up there? What were you going to say?
I was also plug the 8 into the 13x and see what 13 times 8 is.
Right, plug 8 in there, okay, and see if that gives you your 104. Okay, so if I do that, 10 times 8 is 80, 3 times 8 is 24, 80 plus 24 is 104. So 13 times 8 is 104, which is mimicking the 50 plus 54 that we got there, right? Okay. Something that you guys want to pay attention to in your homework tonight is something that is going to look like this, where they give you they'll give you some algebraic expression here inside that angle. They'll give you some algebraic expression inside that angle. Okay? And you see that we should probably add the red one and the blue one together, right? So we go red expression, whatever that may be, add to it, blue expression, whatever that may be, and equal now a total, right? Because we've got to add 2 things up to get the total. What is the total going to be here? 180. Okay? So there's 2 problems, I think, specifically that I saw. One of them says that this angle, maybe we call this angle, put some points in here. Maybe they say A, B, C, and D. They say A, B, C is a straight angle. So that's kind of telling you the 180, that relationship that you need. Okay? There was another one that just gave you the picture, didn't say anything about it. It looks like a straight line, so use it, assume that's a straight line. We'll talk later this week, early next week, about the things that we can assume when we look at a picture and the things that we cannot assume when we look at a picture. That tends to be an issue for a lot of people in this class. Do not make assumptions about a lot of things, but if the line looks straight, okay, like a straight angle or opposite rays or something like that, make that assumption and use that fact right now. Okay? Other than that, I think the assignment, we've gone over an example of everything on there. Remember that my website, guys, if obviously we go through 3 or 4 examples in class, but you get to the website and there's 6 videos there, but that might be a total of, if there's three examples in each one of those videos, that might be 18 extra examples you go through. Okay, so use those to supplement what we talk about in class, especially if you don't understand. Like if you fully understand what's going on, those aren't maybe things that you need to go to. But if you're struggling, asking questions, needing things fixed, get on a homework question, you get stuck, look at those things. I try to identify what's inside those videos with the names above. Some of them are 2 minutes long, some of them are 60 minutes long. Okay? Not saying you have to watch them all. Not saying you have to watch any of them. If I gotta get the 60-minute one, can I scrub through it and try to find them doing examples? Okay? Some of them I've got a lady that does a really good job of just lecturing through notes, just kind of like we do in class. So if you miss a day of class, that's there. I'm gonna put this thing on YouTube, this video on YouTube of the lecture, and see how that goes. But these things are great resources. These applets are here for you to mess around with. Tomorrow I'll show you how you can pull those off and keep them in your folder if you want to. But those are things that supplement the class and help you increase that learning. Remember that Math Excel assignment to do tomorrow. Tomorrow we'll probably just wrap up any loose ends that we have with segment addition, angle addition. Maybe talk about angle bisectors and then go on from there. All right. That's all I've got for you today. I'm gonna get out of here pretty soon. So I'm either going to